Good afternoon. My name is Mark Trevor Bennett, and I am a registered nurse at the St. Luke's Health System. Today I'm going to be doing an experiment that I like to call osmotic walking water. It's a very simple experiment. I'm going to relate it to the pathophysiology of the human body. To complete this experiment, you'll need to complete 7 super simple steps, all the while having fun. So step 1 is gather your supplies. What you're going to need is a cup of hot water. I just pulled this out of the microwave, not boiling but hot. A cup of neutral water. This is just tap water that's been sitting out for, I don't know, maybe 20 minutes or so. Just regular average water. And then a cup of cold water, and this is water with ice in it. You will need your 2 favorite primary food colors. Just some food coloring, your 2 favorite colors. Some salt. This is just regular old iodine salt. A bowl to put it in, a spoon, and some paper towels. So step 1, we're going to put our water in our cups. This is cold water, like I said. Cold water represents a patient with a hypometabolic state. And for this experiment, what it's really going to be discussing is diffusion, osmosis, active and passive transport, and osmotic pressure. That's really what we're going to get at. The hot water cup is going to represent our patient with a hypermetabolic state, such as an infant or a patient with a disease process that has accelerated their body systems. So we now have a cup of cold water, hypometabolic state, such as our elderly patient's hypermetabolic state with an infant. Step 2, we're going to take some salt. So pour a little bit of salt into your cup. The salt is going to represent medications as a nurse administers to a patient. So if we take a spoonful of medication and give it to an infant, without even stirring it, we can see how quickly that dissolves into that solution. Looking at the bottom of the cup, there's hardly any left and we haven't even stirred it yet. Now we're going to take a spoonful of medication and we're going to give it to the elderly patient or the patient with a hypometabolic state that is unable to process medications. I know the camera's kind of far away, but as you can see, the top of the water has not even been disturbed. The bottom, completely covered in a fine layer, almost what I would even consider a thick layer of salt, as none of the salt has hardly even dissolved into that water at all. Now we'll take this and we'll give it a couple stirs, mix it up, heart's pumping that medication around, and with those few simple stirs, there is no longer any salt in this cup, in the hot water or hypermetabolic state. As we start to stir the cold water cup, you can stir and stir and stir, and all there is sediment floating around. This patient is unable to utilize this medication. This patient could be due to kidney failure, liver failure, absorption of the GI tract issues such as colitis, inflammatory bowel disease, lots of reasons why this patient couldn't absorb more than just the natural aging process. Now we've dissolved it pretty good. And then again, in our center cup is just our average patient, just average day, everyday adult. Now we're going to take our food coloring and we're going to dump it into our cup. So our food coloring is we take 2 or 3 drops, represents, we're going to demonstrate osmosis and diffusion. Now as you watch these, the hypermetabolic state just automatically starts working. It's just moving right through the cup. Not even hard, I don't even have to do anything with it. As the cells are excited in that rapid state. In our reduced state, all it's doing is sitting on the top. I mean, it hasn't even gone into the cup at all. Just sitting on the top, stuck. Now, what I want to ask, is this osmosis or is this diffusion how this process works? Is this cup, because it's all processed through osmosis, and this cup sitting just on the top, diffusion? Are they both diffusion? Are they both osmosis? Osmosis requires a semipermeable membrane to transport across it. In neither one of these cups, neither one of them has a semipermeable membrane, which means neither one are osmosis, giving you the answer of diffusion. So as this food coloring is diffused through this cup, we have a nice even distribution, or diffusion. As I stir this one and help give it a little bit of just go, it's able to do the same thing. The only thing is the excitability of the water molecule doesn't help the process. You stir it up, it does. Now, however, if I slide these cups together and I want to demonstrate osmosis, I can add a semi-permeable membrane or a simple paper towel. So what you'll do is you fold it up. These are just half sheets of paper towel, 2 apiece, or 1 large sheet folded into 4s. And you will take one end and you will submerge it in your cold water solution, and it's going to start coloring the paper towel and moving along the semi-permeable membrane. As this does this, we'll dump the other end in the cold water in. Do the same thing on the hot water side. And we have now implemented a semi-permeable membrane helping to facilitate this transport of these water molecules. Now, as this moves and you can see the color changes occur, we have passive transport because the food coloring is just attached to the water molecule, and as the water molecule moves along, so does the food coloring. So just passive transport happening right now. Now, as we can see, our center cup is starting to actually change colors. We got a nice little yellow going on with our primary color mix there. Maybe it'll turn to a purple or whatnot when it gets mixed up really well. But as you can see, color is changing. A little more green than blue, and that's just because, again, the hypermetabolic state has a more rapid transport than the cold water does. Now, if I was to take these out, take a big old drink of this cup here, the average adult, that's all colored up, would it be salty? What do you think? We have put 2 tablespoons of salt in each cup. We've transported the color over to the center. Would it be salty? The answer is no, and you can demonstrate this yourself. It's not salty at all. The reason why is because we're lacking active transport. Active transport is required to move that, just like the sodium-potassium pump in the body is required to have active transport for that process to work. We're lacking that here. We just have passive transport, and therefore we do not have salty water in the middle. Now, the last thing I want to demonstrate is osmotic pressure. So we have this super colored paper towel here, and as I hold it up, pressure becomes greater at the bottom than it does at the top. This is representative of a patient with a poor functioning pump, such as heart failure patients. Now, as this starts to lose color at the top, you can see that it's draining out and moving down to the bottom, just as our blood would in our vessels. Now, this paper towel, just like our vessel, can only hold so much pressure before it starts to leak. Just like our veins do in our arteries, in our lower extremities, with a patient that has pressure building up greater than what is able as sustainable. Therefore, you end up with edema. So as these leak out and the color drains down, heart's not working well, pressure builds up in the legs, pressure exceeds oncotic pressures of the natural aging process at the time. Some people are a little higher than others. Then you start to get leaky vessels, leaving you with edema. It's a super simple project or experiment that helps me understand what's really going on in the pathophysiology of some of these disease processes. I hope that it's helped you. If you have any questions, comments, or concerns, please feel free to field them to me via any means available. I'd be more than happy to answer them or find you an answer if I don't have one myself. Again, hope you enjoyed this. Take care.